Hey guys, Brandon again. We're back, and as I mentioned before, we're going to be talking about Compton scattering and wave diffraction. Just a little recap from the last podcast. We talked about the differences between waves and particles, with particles being a localized object that has some sort of quantitative measurable qualities to it, and then waves being those propagating fields, especially with light being propagating fields of electric fields and magnetic fields, which is why we call them electromagnetic waves. So, jumping right into the experiments. Sorry, I have to actually refer to my little sheets here. Back in 1924, I believe it was. Yes, it was. Really should have done better research. Man with the last name of Compton. Obviously, they always tend to name the experiments after the people who did it. Was working at Washington University, and he was doing some cool experiments with shooting light essentially at particles. I know to some people that sounds a little weird, or not really something you want to waste your time on. Especially when you can do things like, save the rainforest or new energy. But actually, this was a very groundbreaking experiment for all physicists everywhere. So typically before this experiment, we were used to light, obviously interacting with objects. You can see me now because of light. The light comes in, it hits me, and I absorb it, and then I reflect a little bit back. That reflection is actually from the electrons. That this gets a little more into chemistry, something which I won't cover too much. Jumping from level to level because they're all set on preset levels when they're uh, orbiting around the center of an atom, orbiting around the nucleus, and when they jump from one level to the next, they release a certain amount of energy, and that energy then is interpreted as a wavelength of light, as we were talking about before with the amplitudes. So when you get that wavelength coming at you, that's how you see the light hitting, coming into your eyes, and that's how you see what you see. Your eyes interpret it. Brains, if you have multiple, your brain interprets it and then creates the image in your head. So with the Compton scattering, they did something really cool. They shot what's called a single photon. So when you think of light, you typically think of like, oh, a whole big wave of, energy and brightness hitting me in the face. A single photon, think of that as essentially being the single particle of light. Getting ahead of myself a little bit with the wave particle duality, but that's essentially what it is. It's like you grab a band of just a whole handful of spaghetti. You think of that whole handful of spaghetti as a big wave of light. You pull out just a single thing of spaghetti, that's your single photon. So they were shooting a single photon at an electron in particular. And wouldn't you know it, it did something that they never expected would happen. When the photon hit the electron, it didn't just get absorbed and bounced off. What they saw was it's kind of like playing billiards or pool. For those who don't know what billiards is, it should be everyone. So you hit the cue ball and it goes down the table and it hits another ball. Obviously, the cue ball doesn't just kind of vanish from existence and put all of its energy into the other ball. They hit and bounce it part ways in a perfect reflection, 90 degrees between the two. Anybody who's a professional pool player knows these angles, knows how to bounce them off of the walls correctly to get the proper bounce and get the proper angle coming at the balls. Try not to sink that cue ball in the hole. But when they hit the electron with the photon, they got this exact same effect. Now, for people who are so almost religiously believing, or well, in science you say knowing, that waves and light are one. Light is a wave. This should never happen, but it did. So that created the idea that waves are actually particles. The fact that you can hit an electron with a wave and get this scattering effect where the particle goes one way, the wave goes the other. And we know it's not just the electron giving off its own wave in response to having this excess energy, because the particle will actually shoot off to one side and give off that additional wave of just excess energy that's trying to burn off, and then our original wave does in fact bounce off the other way. And they have detectors set up to really kind of see this happening in action. So that completely turned all of physics inside out. And then we have what's called diffraction. Normally I like to have a little setup where I can show you this, but I do have a laser, but my diffraction plating is currently missing in action. If you were to look at it, it just looks like a little flat plastic film, essentially. But actually, it has about 250 little slits going down it per millimeter. So you get enough little slits that's obviously going to seem, it's just going to feel like it's a flat piece of plastic. And when I say slits, it's essentially the same as looking at your blinds. The space between those blinds, that would be your slits. What you do is you take a piece of or a source of monochromatic light, which again sounds complex, but it's really actually pretty simple. You break down the words monochromatic, single wavelength. Well, chromatic doesn't mean wavelength, but a single measurement. So you have wavelength of one color. So that's why you get the laser pointer. Most laser pointers come in red because red is the easiest to make. Again, that's a little more complex than what we're going to cover right now. But you typically just take a red laser pointer because they're the cheapest. And you find or you make a piece of diffraction plating. The original experiments were actually done with only 2 slits. You have the slits about a hair apart, and they're no more than a hair's width in distance. You take your monochromatic light and you point it at the 2 slits. Most people would expect, oh, okay, the light's gonna, shine a flashlight at it, which has a huge source of multiple colors of light. You're just gonna see the 2 slits on the wall, and then all the light around the sheet of paper or the piece of plastic that you're using as your diffraction plating. Excuse me. But when you shoot the monochromatic light at it, you actually get something that's really cool. And something that's kind of hard for me to really demonstrate without my equipment. Well, excuse me again, but I'll do the best I can. So essentially, you have with this diffraction pattern that shows up, you're going to see a line of dots. So you're going to have like a dot here, a dot here, dot here, dot here, dot here, all going out, all evenly, all on each side. It's symmetrically spaced going out, and the dots get further and further apart the further you go out. Now, you're probably thinking to yourself, how the heck does this happen? Well, as we mentioned in the first podcast, waves have measurable amplitudes. So you have your positive amplitudes, you have your negative amplitudes. So let's pretend that these 2 spots are positive and negative. Top of my head and my chin, basically. So what happens is if you add the 2 together, they come to that neutral spot. Because what's essentially, let's say the amplitude is a magnitude of 1. So you have your positive 1 here, you have your negative 1 here. What happens when you add 1 plus negative 1? You get 0. So that's how you create the dark spots in between. And again, you're probably trying to think, well, okay, that's cool math and all, but why does this happen? The answer isn't as simple as you would hope, but actually it is. It's that propagation we were talking about before. When you create the 2 slits, that creates the 2 different sources of light going through. If you ever go to the docks and you see that they have kind of like the wall partitioning off with like the little entrance for the boats, you'll see that when the waves come through that little hole for the boats, it kind of propagates out from that hole. So when you put 2 holes next to each other, you have 2 waves propagating out next to each other, and wherever they cross over, the amplitudes are going to add up. So all the bright spots are actually where the 2 waves are at a peak amplitude of both positive or both negative, which will create your bright spots going across. And then everywhere in between, if you look really closely, you'll see that it's not actually just bright spot, nothing, bright spot, nothing. It's actually fading down to a dark spot, which is where you have the positive and negative amplitude. So using this, we were able to discern that light is in fact actually a wave. But then we create our Compton scattering experiment, and we have this issue of, well, isn't it actually a particle? And that's why they created the theory of light actually being a wave and a particle. And that's how we created wave-particle duality. And that's pretty much kind of the foundation of most physics that we experiment with now. And you can go a little bit further into that with electrons, actually, because they have a similar problem, which I will not reveal in this podcast, actually. I will discuss that in the next podcast. So stay tuned, and you're going to find out about the great mystery of everything that we're trying to figure out with electrons.